National Electrical Code Section 250.24b explicitly prohibits using the grounded conductor, which is typically the neutral conductor, as an equipment grounding conductor or for equipment grounding purposes. This means that in general, it is not permitted to connect the grounding conductor to the neutral conductor in a streetlight handhole. The rationale behind this prohibition lies in the distinct functions of the neutral and grounding conductors. The neutral conductor is designed to carry current during the normal operation of electrical equipment and systems. This current is the result of the unbalanced load between the energized, or hot, conductors and the neutral. In contrast, the grounding conductor is specifically intended to provide a low impedance path to ground for fault currents. A fault current occurs when there is an unintentional electrical connection between an energized conductor and a grounded surface or equipment enclosure. This could be due to damaged insulation, loose connections, or other equipment failures. The grounding conductor's role is to quickly and safely conduct this fault current back to the source, typically the transformer or service entrance, allowing the overcurrent protective device, such as a circuit breaker or fuse, to trip and de-energize the circuit. Connecting the grounding conductor to the neutral conductor would effectively nullify its primary function as a protective measure. In the event of a ground fault, the fault current would have two potential paths back to the source, firstly through the grounding conductor and secondly through the neutral conductor. Since the neutral conductor carries normal operating current, it may already be partially loaded. Adding the fault current to the neutral conductor could overload it, potentially causing the conductor to overheat and damage the equipment. Furthermore, if the neutral conductor becomes disconnected or experiences a high impedance connection, the equipment grounding system could become energized, creating a shock hazard. However, there are a few specific exceptions where the National Electrical Code does permit the bonding of the grounding and neutral conductors. These exceptions are typically limited to specific situations involving transformers and service drops. Section 250.28d of the National Electrical Code addresses the grounding of separately derived alternating current systems. A separately derived alternating current system is an electrical power source, such as a generator or a transformer, that is not directly connected to the building service entrance. This section allows the bonding of the grounding and neutral conductors on the secondary side of a transformer under certain conditions. Specifically, this exception applies when the transformer has isolated windings, meaning that the primary and secondary windings are electrically isolated from each other and is supplied from a grounded system. In this case, the grounding and neutral conductors can be bonded together at a single point, typically at the transformer's secondary terminals or at the first disconnecting means. This bonding ensures that the secondary system is properly grounded and provides a low impedance path for fault currents. National Electrical Code Section 250.36 ATWA provides another exception related to service drops. A service drop is the overhead electrical conductor that runs from the utility's power lines to the building's service entrance. If the service drop is not grounded at the supply end, meaning at the utility pole or transformer, then the National Electrical Code allows the bonding of the grounding and neutral conductors on the secondary side of the service drop. This bonding is typically done at the service entrance, where the service drop conductors connect to the building's electrical system. This exception is intended to ensure that the building's electrical system is properly grounded, even if the service drop is not grounded at the utility's end. However, it's important to note that these exceptions are specific to the situations described in the National Electrical Code, and they do not apply to the general case of streetlight handholds. In most street lighting installations, the electrical system is directly connected to the building's service entrance, and the neutral and grounding conductors must be kept separate. Connecting the grounding conductor to the neutral conductor in a streetlight handhole would violate the National Electrical Code and could create a safety hazard. For typical streetlight installations, the grounding conductor should be connected to a dedicated grounding electrode system, such as a ground rod or ground ring, and should be kept separate from the neutral conductor throughout the entire circuit. This ensures that the grounding system functions properly and provides a safe path for fault currents. It is important to consult the latest edition of the National Electrical Code and any applicable local codes and regulations to ensure that all electrical installations are performed safely and in compliance with the requirements. If there are any questions or concerns about the proper grounding of electrical equipment, it is always best to consult with a qualified electrical contractor or engineer. Understanding the distinction between neutral and grounding conductors is crucial for ensuring electrical safety. The neutral conductor carries normal operating current, while the grounding conductor provides a path for fault currents. Connecting these conductors improperly can lead to dangerous situations, including equipment damage and electrical shock hazards. The National Electrical Code provides specific guidelines for grounding and bonding electrical systems to minimize these risks. These guidelines are based on established engineering principles and are designed to protect people and property from electrical hazards. When working with electrical systems, it is essential to follow these guidelines carefully and to seek expert assistance when needed. Proper grounding is a fundamental aspect of electrical safety, and it should never be taken lightly. The National Electrical Code, or National Fire Protection Association 70, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. The National Electrical Code covers a wide range of topics, including grounding and bonding, wiring methods, overcurrent protection, and equipment installation. It is essential for electricians, electrical contractors, and electrical engineers to be familiar with the National Electrical Code and to follow its requirements carefully. Compliance with the National Electrical Code is not only a matter of safety but also a legal requirement in many jurisdictions. Local and state governments often adopt the National Electrical Code as part of their building codes, making it legally binding for all electrical installations. Failure to comply with the National Electrical Code can result in fines, penalties, and even legal liability in the event of an electrical accident. The National Electrical Code is a comprehensive document that contains numerous requirements and exceptions. It is essential to consult the specific sections of the National Electrical Code that apply to a particular electrical installation and to understand the rationale behind those requirements. The National Electrical Code is not intended to be a substitute for sound engineering judgment, but it provides a framework for making safe and informed decisions about electrical installations. Grounding and bonding are two distinct but related concepts in electrical safety. Grounding refers to the connection of an electrical system or equipment to the earth, while bonding refers to the connection of different metallic parts of an electrical system or equipment together to create a low impedance path for fault currents. Both grounding and bonding are essential for providing a safe path for fault currents and for minimizing the risk of electrical shock. The grounding electrode system is a critical component of the grounding system. It consists of one or more grounding electrodes, such as ground rods, ground plates, or ground rings that are buried in the earth and connected to the grounding conductor. The grounding electrode system provides a low impedance path to ground for fault currents and helps to stabilize the voltage of the electrical system. The size and type of grounding electrode required for a particular installation depends on the size and type of electrical system, as well as the soil conditions at the site. The National Electrical Code provides specific requirements for the installation of grounding electrodes to ensure that they are effective and reliable. Bonding is the process of connecting different metallic parts of an electrical system or equipment together to create a low impedance path for fault current. This includes bonding metal conduits, metal enclosures, metal equipment frames, and other metallic parts that are likely to become energized in the event of a fault. Bonding helps to equalize the voltage potential between different metallic parts, reducing the risk of electrical shock. The bonding conductor is the conductor that is used to connect different metallic parts together. The size of the bonding conductor depends on the size of the circuit conductors and the type of equipment being bonded. The National Electrical Code provides specific requirements for the size and installation of bonding conductors to ensure that they are effective and reliable. Overcurrent protection is another essential aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits and equipment from damage caused by excessive current flow. When an overcurrent occurs, the overcurrent protection device will trip or blur, interrupting the flow of current and preventing damage to the circuit or equipment. The size and type of overcurrent protection device required for a particular circuit depends on the ampacity of the circuit conductors and the type of load being served. The National Electrical Code provides specific requirements for the selection and installation of overcurrent protection devices to ensure that they are effective and reliable. Wiring methods are the techniques and materials used to install electrical wiring. The National Electrical Code specifies different wiring methods that are permitted for different types of installations. These wiring methods include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, non-metallic conduit, and cable wiring. The selection of the appropriate wiring method depends on the type of environment, the type of building construction, and the type of electrical system. The National Electrical Code provides specific requirements for the installation of each wiring method to ensure that it is safe and reliable. Equipment installation is another important aspect of electrical safety. The National Electrical Code provides specific requirements for the installation of various types of electrical equipment, such as transformers, generators, motors, and appliances. These requirements are designed to ensure that the equipment is installed safely and in accordance with the manufacturer's instructions. The National Electrical Code also provides requirements for the grounding and bonding of electrical equipment to minimize the risk of electrical shock. Electrical safety is a shared responsibility. Electricians, electrical contractors, electrical engineers, and homeowners all have a role to play in ensuring that electrical systems are installed and maintained safely. By following the requirements of the National Electrical Code, by using qualified electrical professionals, and by educating themselves about electrical safety, people can minimize the risk of electrical hazards and protect themselves and their property from harm.